Welcome to OPIM 201, Operations Management. Today, we will explore the impact of variability on waiting time problems. Variability is a key concept in operations management. It affects how we manage processes and resources. When we think about waiting times, we often consider customer experiences. Long waits can lead to dissatisfaction. This is especially true in service industries. Understanding variability helps us reduce these waiting times. It allows us to address waiting time problems effectively. First, we will explore how variability affects process flow time. Variability refers to the differences that can occur in a process. These differences can slow down operations. For example, if some tasks take longer than expected, it can create delays. We will discuss how to manage this variability to improve efficiency. Next, we will look at the economic impact of waiting and congestion in business processes. Waiting occurs when resources are not being used effectively. Congestion happens when too many tasks are trying to move through a process at once. Both can lead to increased costs and reduced productivity. We will analyze how these factors affect the bottom line. You will also learn about the drivers of waiting time in processes. Various factors can cause delays. Identifying these drivers will help you find solutions to reduce waiting times. Next, we will explore techniques to predict waiting times in processes. With the right estimates of process characteristics, you can make informed predictions. This skill will be valuable in planning and optimizing processes. We will then consider how waiting times affect staffing plans. Proper staffing can minimize delays and improve efficiency. Finally, we will suggest strategies to reduce waiting times in processes. Implementing these strategies can enhance productivity and customer experience. By the end of this session, you will have a better understanding of these concepts and their importance in business operations. Queues form when the arrival rate of items exceeds the service rate. This means that more items arrive than can be processed in a given time. Consider a toll booth on the New Jersey Turnpike during Thanksgiving. Many cars arrive at once. The toll booth cannot process all the cars quickly. This leads to a long line of vehicles waiting to pay. Sometimes, the arrival and service rates change. For instance, a brokerage may see a spike in calls during certain weeks. The average service rate can handle regular traffic. But during busy times, it may struggle. This creates a backlog of calls. Queues happen when demand exceeds capacity. Understanding this helps us manage processes better. There are two main types of variability that we need to consider: demand variability and process variability. Demand variability refers to the fluctuations in customer demand. For instance, a restaurant may experience a surge in customers during lunch hours, but have fewer patrons during off-peak times. This inconsistency can lead to longer wait times if the restaurant is not prepared to handle the influx. Process variability involves inconsistencies in how services or products are delivered. For example, if a manufacturing line has machines that operate at different speeds, it can create bottlenecks. These bottlenecks can slow down the entire process, leading to delays and increased waiting times for customers. The graph shows the number of customer calls received every 15 minutes throughout the day. During certain times, we notice a predictable increase in the number of customer calls. For instance, around the early morning and early evening, the number of calls rises significantly. These busy periods are expected and help the staff prepare for the influx. However, the graph also reveals unpredictable fluctuations. There are sudden spikes and drops in customer calls that can occur at any time. For example, a rush of calls might appear unexpectedly during a quiet hour. These insights into customer behavior are essential for INSER. By recognizing both the predictable and unpredictable patterns, the team can better manage resources, ensuring they are ready to provide excellent service when it's needed most. An into-arrival time is the time between two arrivals to a process. It helps us understand how often events occur. An arrival process is considered stationary if it remains consistent over a specific period. This means that the expected number of arrivals stays the same, regardless of the time interval chosen. For example, if we look at a day, the expected arrivals in any 3-hour window will be the same, whether we choose the first 3 hours or the last 3 hours. However, processes can also be non-stationary. This happens over longer periods, like days or weeks. In these cases, the arrival patterns may change. For example, a process might be stationary over short periods, like 1 hour or 15 minutes, but not over longer stretches of time. Understanding these concepts helps us analyze and predict patterns in various processes. The graph shows the number of customers arriving at answer over a day. It measures arrivals in 15-minute intervals. You can see that the number of customers varies significantly throughout the day. There are clear peaks and troughs. These peaks represent busy times, while the troughs show quieter periods. The interesting part is that these patterns repeat daily. For example, if there is a peak at 9 a.m. today, you can expect a similar peak at the same time tomorrow. Note also that customer arrivals are non-stationary. In other words, they do not stay constant over time. Instead, they change based on the time of day. Understanding these patterns can help us manage resources better. We can prepare for busy times and ensure we have enough staff available. We will learn about two important parameters used to describe into-arrival times in a process. First, we have the average into-arrival time. This is simply the mean time between arrivals in a process. For example, if customers arrive every minute on average, that is our average into-arrival time. Next, we have the standard deviation of the into-arrival times. This measures how much variation there is in the arrival times. A low standard deviation means the arrival times are close to the average. A high standard deviation indicates more variability. Two different arrival processes can have the same average into-arrival time. However, they can differ in how much their arrival times vary. One process might have consistent arrivals, while another might have arrivals that are more spread out. This difference is captured by the standard deviation. Variability tells us how much data points differ from each other. Imagine two different processes. Both have the same standard deviation. However, they can appear very different. On the left, we see one set of data. This sample has an average of 10 and a standard deviation of 10. On the right, we see another set. This sample has an average of 100 and a standard deviation of 10. When we look at the graphs, the left side shows more ups and downs. This makes it seem more variable. The right side appears smoother, even though both have the same standard deviation. The standard deviation is an absolute measure of variability. But how we perceive variability can differ. Always look closely at the data to understand its true nature. The previous slide showed two processes plotted on different scales for the y-axis. Now, we will look at the plots on the same scale. On the left, we see the first process. Its average is 10, with a standard deviation of 10. On the right, the second process has an average of 100, with a standard deviation of 10. Visually, we can now see the first process is more variable, while both processes have the same standard deviation. Their variability is quite different. The coefficient of variation, CV, helps us understand variability in a process. It shows how much variation exists relative to the average. Imagine we have two sets of data related to into-arrival times. For the first set, the average into-arrival time is 10, and the standard deviation is also 10. To find the CV, we divide the standard deviation by the average. CVA is 1. This result tells us that there is a moderate level of variability in this process. Now, let's look at the second set of data. Here, the average into-arrival time increases to 100, and the standard deviation remains at 10. When we calculate the CV for this set, CVA is 0.1. This lower CV indicates a much smaller level of variability compared to the first set. The coefficient of variation is a valuable tool for comparing different processes. A lower CV suggests more consistency, while a higher CV points to increased variability. Once upon a time in a bustling service center, the team was eager to understand how long their calls took. They wanted to improve their efficiency and better serve their customers. To do this, they decided to explore the concept of service time variability. The team learned about the coefficient of variation, CV, a vital tool for measuring how much the time taken for a service could change. This formula would help them grasp the relationship between variability and average service time. As they delved deeper, they found that the standard deviation of their activity times was 150 seconds. This number revealed how much the service times varied from one call to another. Meanwhile, the average call time stood at 120 seconds. representing the typical duration they expected for each service interaction. With this information in hand, the team calculated the CV. This result of 1.25 indicated that the variability in their service times was quite significant compared to the average. It was a clear signal that they needed to pay attention to how long their calls could take. To visualize their findings, the team created a histogram. This chart displayed the frequency of different call durations. They noticed that while most calls were relatively short, there were a few that took much longer. This visual representation helped them see the spread of service times more clearly. In the end, the team realized that understanding service time variability was crucial for their success. It would not only help them manage customer expectations, but also improve their overall service efficiency. With this newfound knowledge, they felt empowered to make positive changes in their service center, ensuring that every customer received the best experience possible. In a call center, managing incoming calls is crucial. This system shows how calls are handled. When customers call, they may face different outcomes. Some calls are answered, while others are put on hold. At peak times, 80% of calls receive a busy signal. This means many customers cannot get through. Customers who do get through often wait. On average, they wait about 10 minutes. This can lead to frustration. Some customers may even hang up before speaking to a representative. These are called abandoned calls. The financial impact of this system is significant. The call center incurs costs for telephone lines, which total $25,000. Additionally, there are losses from customers who hang up. This includes lost goodwill and throughput. A simple queuing system can show how call centers operate. It highlights the importance of managing calls effectively to reduce wait times and improve customer satisfaction. In an odd and busy service environment, a series of patients arrive at regular intervals. Each patient needs attention for a brief period. Each patient arrives every 5 minutes. They are served immediately upon arrival. The service time for each patient is consistent at 4 minutes. By 8 o'clock, all patients have been served. This process shows a clear, organized but odd flow of service. In this service process, we have 12 patients arriving at different times. Observe that each patient has a specific arrival time and processing time. The graph shows the number of cases processed in different time intervals. It helps us understand how many patients are served within specific time frames. For example, there are 3 cases which required 2 minutes to process, and 1 case requiring 7 minutes to process. With knowledge of waiting time concepts, we can ascertain that 1. The patients arrive at intervals. The average time between arrivals is 5 minutes. 2. Each patient takes a different amount of time to be processed. The average processing time is about 4.08 minutes. 3. The service is utilized at 81.7%. This means that the service is busy most of the time. 4. Patients may have to wait before being processed. This process illustrates the importance of managing patient flow and service efficiency. It highlights how arrival and processing times affect overall service. In a busy healthcare setting, managing patient flow is essential for providing timely care. Imagine a scenario where patients arrive at different times, some quickly and others more slowly. This variability in arrival and service times can lead to longer waiting periods for those seeking treatment. Picture a graph that illustrates this patient flow from 7 o'clock to 8 o'clock. Each bar on the graph represents a patient. The red bars indicate the time patients spend waiting, while the green bars show the time taken to treat them. When one patient takes longer to receive care, it creates a ripple effect, causing the next patient to wait even longer. This situation highlights how variability can significantly impact waiting times. Now, consider the bottom graph, which displays the number of patients waiting at the lab. When the inventory of patients is high, it signals a bottleneck in the system. Conversely, a low inventory indicates a smoother flow of patients through the process. By effectively managing both arrival and service times, healthcare providers can reduce waiting times and enhance the overall efficiency of patient care. In our previous discussions, we focused on resource utilization. We assumed that there was no variability. This means we thought resources were always available when needed. However, this assumption isn't always true. Even if resource utilization is below 100%, flow units can still experience delays. This happens due to two main factors: arrival variability and processing variability. Arrival variability refers to the unpredictable timing of when flow units arrive. Processing variability involves differences in how long it takes to handle each flow unit. Both types of variability can lead to waiting times, even when resources are not fully utilized. It's important to note that demand can build up. When a resource is busy, flow units may accumulate. This accumulation can lead to delays. Even if the resource is not fully utilized, supply cannot get ahead of demand when there are no flow units waiting. This creates a balance that we need to understand. This means that there can be 1. Immediate response. If there are no flow units waiting, it indicates that the supply is currently meeting the demand. This means that every unit produced or processed is being utilized right away. There's no backlog, and resources are not being wasted. 2. No accumulation. Without flow units waiting, supply cannot exceed demand. This prevents overproduction or excess inventory, which can lead to inefficiencies and increased costs. 3. Dynamic adjustment. In a balanced system, supply adjusts to meet demand in real time. If demand suddenly spikes, resources may become strained, leading to potential delays. Conversely, if demand drops, resources may become underutilized. In situations with variability, we often find ourselves in catch-up mode. This means that sometimes we will have waiting units. This occurs even when resource utilization is below 100%. Catch-up mode occurs when demand for resources exceeds the available supply. In this state, resources are not able to keep pace with the incoming demand. As a result, we often see waiting units. These are units that are ready to be processed, but cannot be immediately attended to due to resource constraints. If you enjoyed this content, please consider liking and subscribing. Thank you.